use both? Okay, so what I'm going to present is a joint work in progress with all this bunch of people here. So I'm not going to mention all of them, but most of them are here in this room. So let me begin with the introduction. To say that I'm borrowing this from some slides from Matthias Casselli. There are a couple of paradoxes that most economists now have to explain and that most conventional models don't explain or can't explain. One of them is the following, the fact that, as you know, the public debt of the US is growing tremendously since many years, but at the same time, the spread of the US debt is declining. I don't know any conventional model that is in accordance to that would explain this. First paradox. Second one, as you also know, the monetary basis, that is the quantity of central bank money that is injected by the central banks in the interbank markets is exploding. And at the same time, the domestic inflation is not exploding. And most conventional models would tell you that you should have a huge inflation, if not hyperinflation, given the growth rate of the quantity of money circulating in the economy. Second paradox. Third paradox, this relates to the tragedy in the Eurozone. Here you have the quantitative assessment of the fiscal tightening of each country in the Eurozone relative to its GDP in 2008. So the more you're on the right side, from your viewpoint, the larger was the fiscal tightening. Okay? And at the same time, here on the y-axis, you have fiscal tightening, the reduction in fiscal spending, in public spending. And here, you have the GDP growth since 2008. So the astonishing result is that the more effort you made in terms of fiscal tightening, the less GDP growth you had. And Greece is here, okay? So the more serious you were in terms of fiscal tightening, the less growth you had. So, and most conventional models would tell you exactly the opposite, okay? If you are serious in terms of public finance, you should get more growth. That's exactly the opposite that you observe, at least within the Eurozone. So, third paradox. In addition to all these paradoxes that most conventional models are at pain to explain, we all agree, I guess, in this room that we need new macroeconomic models to assess the role of energy in economics, the impact of climate change, and the feasibility of the energy shift scenarios. Why is energy, I'm going to go very fast here because most of you know this, but just as a reminder, why is energy so much neglected by most conventional economists? Because all of them refer to the so-called cost share theorem, which tells you that under certain circumstances, d'accord, okay. Okay. According to this celebrated theorem, the output elasticity, I mean the GDP elasticity with respect to energy, should be equal at equilibrium to the cost, I mean the share of energy in the GDP. And as we already saw, the share of energy due to the low price of energy is very small, around something like 8% in the US since 30 years, so that most economists would tell you that the GDP elasticity with respect to energy is very low, something like 8%. So as a consequence, most of them would conclude that energy is not a topic for economics. One of these is Olivier Blanchard, the former chief economist of the IMF, who is publishing a paper every 3 years to explain, don't worry, energy is not an issue in economics because of this kind of argument, okay? Now, this theorem can be explained as follows. Suppose that you have, this is a very first week textbook microeconomics lecture. Suppose that you have a production sector which produces Y over there. So this is the output. This is X is the input. P is the relative price of the input with respect to the price of the output. So the production sector behaves as if it was maximizing its net profit, which is the revenue from sales minus the cost of the input. Now, if you write down the first order condition of this maximization program, you will easily get this equality, which is the cost share theorem, which tells you that the share of, let's say, energy, if Y is the input of energy, with respect to the whole cost of producing, let's say the GDP, should be equal to the elasticity of the output with respect to energy, which is this quantity, okay? So which means that if you want an increase of, let's say, 10% of the GDP, according to this kind of theory, you don't need more than 0.8% increase in the consumption of energy, which of course leads to the conclusion that energy is not an issue for growth, okay? Now it's easy to understand that if you go back to this very simplistic model, you just add one constraint, whatever it is. Might be a geophysical constraint, a political constraint, whatever. So now you face maximization program, profit maximization program, plus some constraint. Now if you write down again the first order conditions, you get this. And these are, as you know, the lambda, the shadow prices, or the Lagrange multipliers of the constraint maximization program. Now, if they are equal to 0, you recover the cost share theorem. If they are not equal to 0, you may have a perfect decoupling between the elasticity here and this quantity here, okay? So you may have a very low cost share of energy with a very high elasticity. That's perfectly compatible, okay? Now, this points towards, yes, and this argument, as far as I know, was first put forward by Bob and Rainer Kümmel. Now, this points towards, could we estimate empirically the elasticity of GDP with respect to energy? This is what we did with Zeynep Karaman from the SHIFT project. And we ended up with the conclusion that the elasticity, actually it's dependency, but I don't go into the details here. The elasticity is rather around 60%, not 8%, but 60%, okay, on average for something like 40 countries from the OECD for the last 40 years, okay? Which means if you want to have a 10% increase of your GDP, you need a 6% increase of your consumption of energy on average, which matters a lot, okay? Is that clear? No question? And this was also confirmed by completely different techniques using the Bayesian estimation of a DSG model, entirely conventional DSG model. Now, another point still in this introduction that I want to stress, which is the role of prices. In most conventional neoclassical models, you would have the faith that prices at a certain point should reflect the scarcity of resources. Let's say, if you think in terms of the Hotelling model, it will tell you that if coal is going to be scarce, then the price of coal should explode at a certain point, okay? As an echo of the fact that it's hard to find coal, okay? Now, suppose that the price of the resource you are looking at, let's say oil, is financialized in the sense that you have a lot of financial markets where you can trade, let's say, futures on oil, and suppose you put a lot of capital on these financial markets, as it is the case today. As you know, the financial weight of the market for futures on oil is 30 times larger than the market for spot oil, okay? So when capital moves on the financial market of oil, on oil, this has great impact on the spot market for oil, okay? Whatever being the demand or the supply of oil, okay? Now suppose that because of this financialization, the price of your resource is not given by, let's say, some exponential growth as it would be were Hotelling right, but the same trend, so the deterministic trend which reflects the scarcity of the resource plus some Brownian motion, okay? And suppose that the volatility might be very high compared to the trend, the underlying deterministic trend, okay? So if the volatility is small, you will get something that follows the deterministic trend with some volatility. So in this case, the price will reflect more or less the fact that the resource is getting scarce, okay? But now if the volatility is high enough, okay, if the volatility is high enough, then you may have this diffusion process that converges to zero, even though the deterministic trend is exploding. Okay? This is a result by Boulot and Giraud, two friends, which is quite counterintuitive the first time you see it, but not very difficult from a mathematical viewpoint. So which means you may have today a very low price of oil because the price of oil is entirely financialized. Okay? So the conclusion of that is that we cannot trust prices as a guide for macroeconomic policy. So still in the criticizing a little bit the neoclassical models, and since I gave a conference 2 years ago on this same topic, I won't go into the details. Most neoclassical models don't have energy as a production in the production function. They don't have matter either. They don't have money. Maybe that's more surprising, but they don't have money. In most of these models, we are just trading. You know, it's a barter trade model where money doesn't matter. You have no out of equilibrium dynamics. Okay? In most of these models are equilibrium models where we assume to begin with that we are already at equilibrium and we will stay at equilibrium until the end of the history of mankind. Okay? As a consequence, even the distinction between stocks and flows is hard to make in these kind of equilibrium models. Okay? Because everything being at equilibrium, you cannot distinguish easily what is a stock and what is a flow, which from the viewpoint of physicists is really intriguing, to say the least. You don't have any emergence phenomenon, meaning that these kind of models don't take into account the fact that by aggregating the behavior of millions of people, you may have an aggregate behavior that cannot boil down to the behavior of a single individual. Eva has produced some beautiful papers on this issue. This issue is well known even within conventional economics, but most of the models that are used in macro don't care. And they assume, let's say, that you have a representative household or a representative firm which behaves in the same way at the individual level and at the aggregate level, which of course is probably stupid. You don't have, or you hardly have, some nonlinearity or some non-Gaussianity in the presumed dynamics when there is a little bit of dynamics. Here you can think of the DSGE models. All these models are linear and Gaussian. And probably we suspect that real life is neither linear nor Gaussian. In most of these models, you don't have any private debt. This sounds surprising, but it's so. There is one exception, which is the beautiful paper by Krugman and Ingersoll. But in this paper, there is no money. So people have debt, but they don't have money. Okay? Neither do you have any banking sector. Sometimes you have some animals that are called banks, but these are financial intermediaries. These are not banks. A bank is an institution that can create money. And in most of these models, you don't have money creation by banks. So you don't have banks. You don't have underemployment, at least when the labor market is perfectly flexible. If in these models you find underemployment, it is because the labor market is not flexible. That's why most of these economists would tell you, if you want to fight against unemployment, you need to make the labor market more flexible. So you need to suppress the French so-called CDI, etc. Okay, the minimum wage. All this makes the labor market not flexible. Okay, why? Because in this kind of model, if everything was perfectly flexible, you would never have unemployment. Okay, and there is never. I mean, people never have bad surprise in this kind of model because of the hypothesis of rational expectations, which says that having all the information that we can have today, everything goes as if economic actors would perfectly anticipate the future, or would perfectly anticipate, the conditional expectation of every random variable given the information of today, which of course is never met in real life. Okay, so this means that a crash like 2008 can never occur in this kind of model, except as a black swan that is, as you know, in the tail of a distribution with a very, very, very small probability, so that nobody cares. Okay? So what we want to do is exactly the opposite. We want to have a truly dynamic...
Will you tell us at the end of the speech what these models are designed for? You said all that they don't do. Is it possible to know what they do?
Well, you should ask to some conventional economists.
And if the answer is to impress your colleagues with your mathematical prowess.
Maybe, yeah. Okay. So what we want to do is to have a truly dynamic model that is stock flow consistent. Stock flow consistent means that, I will go back to this, that you have a sharp distinction between stocks and flows, and that you make sure that the stocks are indeed the outcome of the flows. Okay? It is as simple as that. But even this consistency requirement is not necessarily met in all the conventional models. You need it to be multi-sectoral, meaning that you can make a distinction, let's say, between agriculture and industry, which very often you cannot in conventional models. You need this model to be empirically estimated and simulated, which is not necessarily the case in general equilibrium models. You want this model to have money, and money that is non-neutral in the sense that the quantity of money injected into the economy matters for the economy. Okay? You need also to have this model with endogenous money creation by banks. You must allow for the possibility that there might be mass unemployment. You must allow for the possibility that financial crashes can be the source of real shocks, which is almost never the case in conventional models. In conventional models, at most, what you may have is a real business cycle, which in the depressive phase of the cycle will induce some financial crash. Never the opposite, or almost never the opposite. But what we saw in 2008 was a purely financial crash that apparently didn't have any real business cycle origin, and that was the origin, the source of real shock. Okay? Yes?
How can you simulate a financial crash if you have no money in the bubble?
Oh, yes, that's interesting. You may have some assets on tomatoes and oranges.
Okay.
Okay. Now, you need also, I won't go into the details of that because it's not our topic today. There are beautiful papers by Joe Stiglitz which try to reformulate the whole issue of inequality, and where he underlines some new stylized facts on inequality. And we would also like this kind of family of models to be able to give a rationale for these new stylized facts. You want also private debts to matter, and in particular debt deflation should be able to occur in this kind of model. Now, you need also various sectors, including energy and other natural resources. So you need an input-output analysis. We want the dynamics of EROI to be taken into account. We want to have also climate back loops and the new started facts about inequality. Okay? So this is the program. Now, a starting example. So let me begin with the Goodwin's paper, which is an old paper from the 60s, which is just a mere adaptation of the Lotka-Volterra, pre-predatory dynamics in economics. Okay? So suppose, these are very simplistic assumptions, but it's just to help us understand what's going on. Suppose you have the production QT, which depends upon labor and capital in this very, very simple way. This simple way means that you have no substitution between labor and capital, just for simplicity, for the time being. Okay? So this is a standard Leontief production function with just capital and labor to begin with. Okay? Suppose, suppose in addition to that you have a weak efficiency requirement, that is you just hire the exact amount of people needed given the quantity of capital you have, so that you don't lose money by hiring too many people or having too many capital. So you are exactly at the position where you have an equality between these three elements here. Suppose also, just for simplicity, that the productivity of labor, which is here, grows at some deterministic rate, and that the demography, the quantity, the labor force that is available also grows at an exponential rate, which is deterministic, just for simplicity, okay? Just in order to be able to do some math for the time being. Now here, LT is the quantity of labor employed, so this is the ratio between labor and labor force. So this is the employment rate. And suppose you have some very simple short-term Phillips curve of this way. The growth rate of wages is here, just for simplicity, a linear function of the employment rate. Meaning, if you have a lot of employment, then it's easier for employed people to bargain for an increase of the wages. If you have a lot of unemployment, then it's harder to get some increase in your wage. Okay? As simple as that. Now you define the wage share, which is just the ratio between the output and the whole wage bill here, okay, which is roughly 60% in most countries, most OECD countries. The profit share is just the opposite, okay? And investment here is just defined as being exactly equal to the profit. So for simplicity here, we just assume that the firms invest all the profit, okay? Of course, we will relax all these assumptions in a few minutes. So investment exactly equal to saving. We assume also sales law, that is, the consumption will exactly adjust so that supply equal to equal demand, and we have the capital accumulation equation, which is standard. Now, this very simplistic model can boil down to a two-dimensional dynamical system where you have two variables that drive the whole model, the whole dynamics, namely the employment rate and the wage share. You see that this is a nonlinear dynamical system, two-dimensional, which is conservative. Oh. Okay, and so you have this kind of phase space diagram where you have here omega, the wage share, lambda, the employment rate, and a solution or trajectory follows this kind of path. Here you have the output, the GDP, let's say, which has an endogenous cycle and some growth here, very simple, okay? Of course, nobody believes in this model. It's just to help us understand what's going on. Now, if you remember that for simplicity, I assume that the short-run Phillips curve is linear here. Of course, you could choose another one. So Grasselli and Costa Lima have chosen this kind of function, slightly different, and this leads to this kind of dynamics, slightly different, okay, GDP. So then the question is, which investment function should we add, should we take? And the answer we want to take here is to say, let the data speak. So what we're going to do is not to imagine, because we are clever economists, what the investment function should be. We are going to estimate this investment function according to the data. For this purpose, we are going to use some gamless methodology, which is a polynomial approximation with non-Gaussian residual of the link between investment and, let's say, wage share, profit share, employment, etc. Okay, this is a methodology that has been developed by Vlasios Voudouris a couple of years ago, and then we can run some Monte Carlo simulations. Okay. In addition to that, you have some money, as I said. So let us introduce inflation. So of course, you may have a Phillips curve that depends upon inflation to a certain amount, which measures the money illusion. And the dynamics of prices will be given by some relaxation dynamics towards the unit cost of production, which here is just labor for simplicity, some markup. And here you have a relaxation parameter, which tells you how fast the price will relax to the unit cost of production, okay? And the markup is just due to the fact that we implicitly assume that there is imperfect competition on the commodity market, and this relaxation parameter is the analog of the Calvo parameter that is used in DSG models, okay? In addition to that, I won't enter into these details, but you also can prove that you have some endogenous money creation in this model. Next point, in order to relax one after the others, all the assumptions that I just mentioned at the beginning, you can replace the Leontief production function where there is no substitution between capital and labor by some CES, constant elasticity of substitution production function, like this, where you may have some substitution in the short run between capital and labor, okay? The advantage is that then if you use this kind of production function, then you get a unique globally stable equilibrium, okay? The dynamical system becomes structurally stable in the sense of Steve Smale, okay? And it better fits the data. So let me say one word about, in addition to that, if you take the CES production function like this, it turns out that the capital output ratio is no more constant. It's given by this. And empirically speaking, what we observe is that the capital output ratio is never constant. So it better fits the data. Let me say some word about how we can fit the data with this very, very, very simplistic model. If you go back to the most famous neoclassical growth model, which is the Solow model, as you know, there is a huge literature claiming that the Solow model fits very good the data. The point is that all this literature is flawed because it's based on an accounting tautology. Okay, probably you know this. I don't have time enough to go into the details, but there are at least three papers which make the demonstration that most econometric proofs with quotation marks of the fact that the Solow model is accurate and fits the data. These three papers show that all this literature is just flawed. Okay. Now, if you look at this, you see that this is just for the US, the GDP growth, GDP. You see that if you just take an exponential function, it fits very good the data. So we could as well replace the Solow model by just a deterministic exponential function. And if you take a 3.5% growth rate, you have an error square of 0.98. So the best macroeconomic model is just an exponential function. Now, people like Solow have claimed that the Goodwin model I just described 2 minutes ago poorly fit the data. And there is a methodological debate on this issue. So after Solow, you had Harvey, who tried to give the same demonstration. And this would be a good point for neoclassical economists. But the point is that Grasselli showed that there was a big error in Harvey computation. Correcting this error makes the Goodwin model much more accurate to the data. And actually, Florent Maquisac has shown a way to estimate the model that makes it very accurate to the data. Let me just explain how we do this. So you estimate the behavioral function, that is investment and the Phillips curve, according to this Gamless methodology, that is nonlinear, polynomial, and non-Gaussian. And then you estimate the nonlinear reduced dynamical system using a maximum likelihood techniques. Now, there is a big problem due to the fact that in macroeconomics, at variance with what you have in physics or what people have in finance, you have quarterly data. You don't have data for every nanosecond. Okay? This means that the data you have are intrinsically discrete data, and the model we have is a continuous time model. So there is an issue on the way you can estimate a continuous time nonlinear dynamical system on discrete data. So in order to overcome this problem, what we use is that we use some Brownian bridge and Monte Carlo techniques. I don't enter into the details, but once you have done this, this is the way you can simulate lambda, that is the employment rate in the US. So this is numerical simulation. This is historical data. Now, if you do some back testing, that is, you take the data until, let's say, 2000, I don't remember, 2012, let's say. You run your model and you compare what you observe with your model with what you really had. You try to see whether you are accurate. Then it turns out that the rate is the prediction using the Goodwin model. And this magenta, or how you call this in English? Purple, exactly. This purple curve is obtained using a VAR, vector autoregressive model. I don't know whether you are familiar with the VAR model. VAR is the most commonly used macroeconomic prediction model, which is purely statistical. Okay? And most macroeconomists would tell you if you can do as good as a VAR, you are 100% accurate in empirical terms. Okay? And it turns out that here we do better than a VAR, even in the short run. This is the prediction of the VAR, which just after 1 quarter is wrong. And we are wrong, but a little bit later. Okay? Of course, you might say, well, it's not fantastic as a result, but I can tell you that for macroeconomists, I mean, at least for me, it's the first time I see a model that does better than a VAR. Okay? So this shows that even using such a simplistic model as the Goodwin model, 2-dimensional dynamical system, you may do better than the best technique that macroeconomists use so far to predict the future, the next quarter. Okay? So this is what we do. And then this is a comparison between the VAR and our model. And The red line is the error forecast, the forecast error of the VAR. The black line is our own forecast error, and on average we do much better than the VAR model. Okay, then Adrien, who is here, conceived a stochastic extension of this Goodwin model. I don't go into the details. If you have questions on this, you can ask him. Now, if you try to, okay, this was just the Goodwin model. Now I have to jump from Goodwin to Keene a couple of years later, which did the following. Steve Keene introduced depth into this very simplistic two-dimensional dynamical system. By doing so, he also plunged Goodwin's model into the family of stock flow consistent models. That is, you could also start everything I said, by looking at this balance sheet, writing down the correct flows and stocks for the economy, where you have households, firms, banks, and the total here. And then you could play with this table and try to think of some dynamics which will explain how the flows of transaction and the flows of funds behave in such a way that it remains consistent for the whole economy. Okay? Now, I don't go into the details of that. Let me just mention this. What Keene did is to say, okay, assume that the investment function is just a function of the profit share that might exceed the profit of the firm at time t. Okay, so suppose the production sector wants to invest more than its current profit. Then it needs to borrow money to finance the surplus of investment. Okay? From where is this money borrowed? From the banking system. So which means that now the productive sector has a debt, a private debt, whose dynamics is given by the difference between investment and profit. Okay? Now if you do this, which is very simple, you end up with a three-dimensional dynamical system that you can study in the same way I did earlier for the Goodwin model, which is now a dissipative system where at each time t, a fraction of wealth, which is the debt servicing of the productive sector, is pumped out of the system by the banking sector. Okay? Now what happens here in this kind of three-dimensional model, you have this kind of dynamics. So here this is the debt output ratio. Here you have the employment rate, and here the wage share. So the story begins here, and you converge to some equilibrium here. This is a good situation. Okay? Now, okay. So you may also have a crash, in the sense that
in the marvelous curve that you showed,
yes,
the line follows the time.
No, yeah, exactly. Time goes around this line.
Okay.
Yes, exactly.
That's the down the toilet.
Okay, using the same kind of dynamics, you may have a crash. Okay, I don't spend too much time on this since I still have just 10 minutes. Okay, now since you may have a crash, you may ask, okay, what you have in general is that in these kind of dynamics, what has been proven is that you have one equilibrium with a crash and finite depth, which is locally non-stable, so we can disregard it. You have one equilibrium without crash, a good equilibrium, and one equilibrium with a crash, and infinite depth, okay, which is also locally stable under reasonable assumptions. So which means that to begin with, in this kind of approach, you have multiple equilibria. Some of them are good, in the sense that you don't have a crash. Some of them are bad. And the big question they can raise is, to which basin of attraction do we belong to? Are we now currently moving into the basin of attraction of the bad equilibrium or of a good equilibrium? Okay? And then you can raise very interesting public policy issues, which are, for instance, is it possible for the state to drive the economy towards the good basin of attraction? Okay? Now, you may also have some turbulence phenomena with this kind of model, where you have the calm before the tempest, which is exactly what you observed before the 2008 crash. We had the great moderation, the volatility of unemployment, inflation, everything went to zero. And at a certain point of time, you remember Larry Summers said, "Oh, triumphatically, oh, we won the battle against volatility." Remember that? Actually, he was just here before the tempest. Okay, so you may have all these kind of phenomena which are well known in hydrodynamics. So this is Pomo-Manville turbulence. but which are hardly known from economists. Now, if you are the government, I don't go into details, you may ask the government to fight against, to have a counter-cyclical policy which fights against the bad cycle in case you would converge to a bad equilibrium. So in this case, suppose here you have the debt to output, private debt to output of the economy, and this is the small cycle we had earlier, but this is the large cycle due to the intervention of the state, okay? So mathematically speaking, everything goes as if you would have a dynamics on the torus with a big cycle, which is the public intervention, and a small cycle, which is the endogenous real business cycle, okay? So in any case, I don't have time to go. In any case, in this kind of model, of course, the Ricardian equivalence theorem with quotation marks fails. This famous theorem tells you that it's useless for the state to spend money because whatever the state is doing, households having rational expectations perfectly anticipate that the additional public spending you are putting into practice today will induce some increase in taxes tomorrow. So they save money to pay taxes tomorrow. So this compensates for the additional public spending. This is the kind of ridiculous theorem that people have to learn in economics to explain why it's useless to have a state in a nation. Okay? So here it's very useful to have a state which may have counter-cyclical impact. My viewpoint is that we should study public policy according to optimal control theory within this kind of dynamics. You can also use some viability theory, and in any case, we should be able to allow for public investment, at least for the energy shift, okay? I don't have time to go into the details. Now, let me jump to, so what I described so far is Goodwin, then Goodwin-Keene, you add debt, prices. You may add banks. I did it with one of my students, so we wrote a report for the European Parliament explaining the cost of the next banking crash in the Eurozone with this kind of model using an explicit sector for the banking system. You may have inventories. This has been done by Adrien. In case you drop the sales law, which says that supply is always equal to demand, then you may have some inventories. So this complicates a lot, of course, the dynamics. You may also have a government, which is useful. You may have a financial market. You may have heterogeneous households. This is a paper I wrote with Matthäus, where you can rewrite the whole theory by Piketty in a better way than he did. And you may have a multi-sectoral extension, which is what I'm going to present now. And finally, climate back loops. This is what Katja is doing, and an open economy. Okay, what I'm going to present in the next 7 minutes is just 5 minutes. It's just how you introduce matter and energy in this model. The starting point is that we suspect, as Ugo Bardi does and as Philippe Biwix does, that there is a vicious circle between energy and matter. In order to have more matter, you need more energy to extract matter. So which means you need more energy here. But because of the EROI issue, in order to have more energy, you need more energy already, okay? And it might be the case also that in order to have more energy, depending upon your energy mix, for instance, if you have a lot of renewable energies, you need also more matter. It might be the case that we might be unable in the next future to be able to overcome this kind of vicious circle. So how do you do this? So briefly, you extend the dynamics I just described in a multi-sectoral manner so that now the basic stone of the model is an input-output matrix. In this input-output matrix, like here, you have here the quantity of item 1, let's say capital, that is needed to produce 1 unit of capital. So actually this is 1 over the EROI or the GROI, in case you are looking at number AGG on the diagonal, okay? And here this is the quantity of item 2 you need to produce item 1. Now you can replace each item. Let's say this is matter, this is energy. So here you have the quantity of matter needed to have 1 ton of matter, let's say copper. Here you have the quantity of energy needed to have 1 unit of energy, okay? And here the quantity of energy needed to have 1 ton of matter, etc. Okay? I don't have time to go into all the details. Okay. Now, using this, it turns out, and that's obvious intuitively speaking, that if you have, let's say now we are in a three-dimensional system where you have three items, let's say consumption good, capital, consumption good, matter, and energy. Depending upon the entries of this matrix, the dynamics will be entirely different. Of course, the more frictions you add in this matrix, the more debt most people will have in order to be able to finance their investment, their consumption. Okay? Now here, for instance, you have just very little friction, and then in this dynamics you end up with, I don't succeed in reading, something which is, the private debt ratio is something below 1. Okay, so you have less than 100% private debt ratio. Now, if you use this matrix, you end up with something which is 350% of debt ratio. Okay, so just by playing with this matrix, you can have a huge influence on the dynamics of the economy, which means the quantity of energy that is needed to have 1 ton of copper matters a lot for the dynamics of the economy. Okay. Now, how can we, the big question we have today, and that's why this is still work in progress, how can we compute this matrix? So actually we have two schools within our small tribe. One school says that, actually 3 schools. One school says that we should use an economist approach where the entries of the matrix are the standard sectors that are used by macroeconomists. So you would have the agricultural sector, the industrial sector, etc. So this we are doing it now for Brazil, and the model for Brazil should be ready at the end of this month, normally, at the end of March, okay? The issue is that if we use this approach, then within the matrix, the input-output matrix, we use prices, okay? In the same way as you did in order to compute the EROI, there are ways to compute the EROI which relies on prices. But as I just mentioned at the beginning, I'm very reluctant to trust prices in the sense that I'm not sure that market prices really reflect the scarcity of natural resources. So if we could calibrate the matrix without relying on prices, this would be much better, okay? Second school says, okay, let's try to write down this matrix without relying on prices. And for this purpose, let's assume, for instance, that you have copper, energy, capital for copper, and capital for energy. So we know that in order to extract 1 kilogram of copper, you need 50 megajoules of energy. Here you have the EROI, 1 over the EROI for energy. The question is how many, or which amount of copper do you need to have 1 kilojoule available for you? This we don't know for the time being. But fortunately, you will have a beautiful talk in a couple of minutes by Olivier, I guess, on EcoInvent, where we virtually have everything we need. I hope so, at least, okay? You will know more about this in a couple of minutes. To this, you couple the dynamics that has been, this is again a Lotka-Volterra dynamics on the resources and the capital. So you say that the quantity of copper you can extract at each time is a function of the quantity of capital installed and the reserves that are available. And the dynamics of the capital itself depends upon the investment minus the depreciation of capital, okay? If you use this, and if you put the right function of investment, you get some Herbert curve on copper. So this is here a Herbert curve on oil, but you could get the same for copper or for energy, okay? It might be the case that due to the fact that investment here depends upon the whole economic dynamics, you may at a certain point have overinvestment or underinvestment. For instance, if the economy is trapped in a deflationary phase, as it is today in Europe, you may have underinvestment, in which case you won't get this beautiful Herbert curve, but something which is below that, with a plateau, for instance. You may have all these kind of things. So this is the first school. Second school, I'm going to say this very rapidly because otherwise they will be furious. Suppose you have 4 sources of energy: nuclear energy, fossil fuel, renewable for thermic purposes, renewable for electricity. Okay. Suppose you have also, I'm going very quickly, 4 final usages: heat, high temperature, low temperature, fuel, electricity. You can write down the link between usage and source, which reflects the energy mix of the economy. For instance, in France, to have electricity, to produce electricity, you need at 80% nuclear energy, 10% fossil fuel, 10% renewable energies. Okay? So the link between the usages and the sources, this is a way to describe the energy mix of the economy. Then you need also, of course, the link the other way, that is the quantity, the fraction of each usage that requires each source. You do a little bit of algebra and you can compute the matrix which links all the sources together, which is this matrix. Suppose you can compute it, then you could plug it in a Goodwin-Keane model in the way I described it earlier, and you would have a full-blown economic dynamics using the 4 types of energy and having the physical relationship depending upon the energy mix between each kind of source and each kind of usage of energy, which would not rely upon prices. Okay? Then you plug this into the economic dynamics I just described. You should be able to analyze, energy shift scenarios for France or for whatever country you like, or even at the world level. So this is the kind of project we have today, and I'm stopping here. Thank you.